Welcome to our lesson on derivatives, the engine of AI learning. Today, we're diving into the mathematical backbone that powers almost every advanced AI system you encounter. Whether you're building a simple machine learning model or working with cutting-edge deep neural networks, understanding derivatives is absolutely fundamental. By the end of this session, you'll have a clear grasp of why they're so critical and how they function behind the scenes. Specifically, you will, first, understand the fundamental role of derivatives in AI and machine learning. Second, grasp core concepts like rate of change, the gradient, the chain rule, and partial derivatives. Third, appreciate how these mathematical tools actually guide AI models toward optimal performance. And finally, you'll connect these abstract mathematical concepts directly to real-world AI applications. Let's begin our journey into the core mechanics of AI. Think of derivatives as the GPS system for AI. Just as your phone's GPS calculates the fastest route by analyzing the slope of different paths, AI systems use derivatives to find the optimal solution by following the steepest descent down an error landscape. Every time a large language model like ChatGPT generates a response, or a recommendation system suggests your next show, derivatives are working behind the scenes, guiding the AI toward better predictions. In machine learning, we're essentially playing a massive game of hot and cold where the AI tries to minimize its mistakes. Derivatives tell us precisely which direction leads to colder, meaning lower error, and how big of a step to take. Without derivatives, AI systems would be like ships without compasses, randomly wandering instead of systematically improving. They are absolutely essential for training complex AI systems and enabling them to learn effectively. This guidance prevents aimless exploration and ensures purposeful improvement. Let's break down some core concepts, starting with the derivative as a rate of change. A derivative simply measures how fast something changes. If you're driving and your speedometer shows 60 miles per hour, that's the derivative of your position with respect to time. In AI, we use derivatives to measure how fast our model's error changes when we adjust its parameters. It tells us, if I change my prediction by a tiny amount, how much will my error change? Now, in real-world scenarios, many factors influence an outcome. This is where partial derivatives come in. When you're cooking, changing the oven temperature affects cooking time, but so does the altitude or humidity. Partial derivatives let us isolate variables, asking, if I only change the temperature, keeping everything else constant, what happens to my cooking time? This helps us understand which parameters matter most, allowing us to focus our optimization efforts where they'll have the biggest impact. While a single derivative tells us about one variable, real AI systems adjust millions of parameters. This is where the gradient comes in. It's like having a multi-dimensional compass. Imagine you're on a hiking trail in a dense fog, trying to get to the lowest point in a valley. You can't see far, but you can feel the slope under your feet. The gradient is like having super sensitive feet that can detect the steepest downward slope in any direction, telling you the optimal way to adjust all parameters at once. Next, we have the chain rule. Modern AI systems are like complex assembly lines or Rube Goldberg machines, where the output of one process becomes the input of the next. The chain rule lets us trace how a small change at the beginning ripples through the entire system to affect the final result. In neural networks, this is crucial for backpropagation, allowing us to figure out exactly how adjusting the connection strength between neurons affects the overall prediction accuracy. We've covered some powerful concepts today. To quickly recap, we learned that derivatives are absolutely fundamental to AI optimization, acting as the GPS that guides models to minimize errors. The gradient gives us that multi-dimensional compass, pointing to the steepest descent across many parameters simultaneously. And the chain rule is what connects the dots in complex systems, allowing changes in early layers of a neural network to influence the final output, which is vital for deep learning. Understanding these mathematical tools isn't just academic, it's about gaining a deeper intuition into how AI learns and how you can build more effective, robust models. To test your understanding, How might understanding derivatives improve your approach to debugging a slow converging machine learning model?